So now that we have the stage set, we've got our formulas in order and hopefully our understanding, let's do some word problems. And homework. So my first example is we're going to have to find the linear speed v, given that you are at a point on the edge of a circle of radius 12, you're doing 3/4 of a revolution in a half second. Right? So that is a mouthful. So what do we know about our linear velocity? Well, we know, right, it's related to our angular velocity, and we know it's our distance divided by time, right? But in terms of the language given, right, we're given a radius, we're given a revolution, and we're given time. So this guy right there is probably not going to make a lot of sense because we're really not given a distance, but we are given a radius, and we are given enough information to find my omega. So in this case, right now, r is equal to 12. So the thing we have to deal with, the thing that's challenging in this particular problem, is what's our angular velocity? Because if I have that, throw it into the formula, I'm finished. So angular velocity, well, we're told we're going through 3/4 of a revolution in a half seconds. So there's our time, but this isn't really an angle yet, all right? But it's going to be pretty easy to do, right? Because we know that one full revolution is 2 pi. And what we're doing, though, is only going through 3/4 of a revolution. So one full revolution times how much of a revolution I've occurred gives us what my theta is going to be. And so in this case, right, what we end up getting, if we do a little bit of math here, theta is 6 pi over 4. And of course, that simplifies to 3 pi over 2. Right? So basically, there's my theta, and we're given our time. So our omega is theta over t, and so in this case, we get 3 pi over 2 is my angle, and it took us a half second to get there. Taking a fraction, dividing by a fraction, we multiply by reciprocal, and we get 3 pi. So our angle of rotation, our angular velocity, is basically 3 pi rads per second. So we're ready. So using our formula now, v equals r omega. Our linear velocity is my radius, that's 12, times my angular velocity, which is 3 pi. Of course, this is in inches, and this is in rads per second, right? And again, rads is actually a unitless, right? It's something we use just to kind of get a feel for what's going on. So when you're done, right, you end up, your linear velocity is 36 pi. Radians being unitless, we end up with inches per second, which is essentially, right, a distance over time, which is what we expect for our linear velocity. So a lot going on there. Even though we have a very relatively simple formula, right, we had to kind of think through some things, especially for our angle, which impacted our angular velocity. Once we got that all in order, we're off to the races. So 36 pi inches per second. Of course, if you wanted to know in terms of, I'm going to reach for my Desmos here. All right, so if we go to Desmos, right, this is 36 pi, right, which looks like it's roughly, right, the velocity is 113.0973 inches per second if you wanted an estimate, right? So there's the exact value, which you guys should be getting used to showing me, and then its corresponding decimal approximation to 4 decimals, which you guys should get used to showing me. Alrighty, so next problem, we're now considering a point on the edge of a tire that has a radius of 16 inches, and we're given the linear velocity is 36 inches per second. So making sense of all this, we know my radius is 16, and we know that my velocity, this is in inches, and we know my velocity is 36 inches per second. All right, so the good news is our distances are measured in the same unit, so we don't have to worry about any conversion factors there. What they're asking us to do first is to find the angular velocity. Well, that's easy, right? So doing that one, we know that v equals r times omega. right? We're given v, it's 36. We're given the radius, it's 16. And so we can basically solve for our omega. Doing a quick division on both sides, we get omega equals 36 over 16. I think you can divide both by 4, and we get 9 over 4. So omega is 9 over 4. And again, it is unitless because we technically took inches divided by inches, but it's understood that this is rad per second. So we're rotating at 9/4 of a rad per second, or roughly about, what is that, 2 1/4 rad per second. So it's pretty fast when you kind of think in terms of 2 radians is roughly about 120 degrees. So we're going through about a 120 degree rotation in 1 second. All right, so relatively fast. So that's A. B, they want us to find the central angle generated by the tire in 4 seconds. All right, and so in this case, right, what we have in terms of the central angle is we know that my angular speed is equal to whatever that angle is divided by unit time. And so doing one quick thing here, we know that the angle that I'm looking for is my angular speed multiplied by the time. And I've got everything we want, right? Here's my omega, there's my time. So the central angle that we sweep out is 9/4 times 4. And so this theta would be 9 radians. All right, so the central angle that's swept out would be 9 radians long. All right, if we went in 4 seconds. Okay, so we're actually, 6.24 is 1 full rotation, 2 pi. So we're actually, almost 1.5 spins around a central angle if we think about that. Alrighty, so there's your first glimpse at using our handy dandy formulas that gives us linear velocity, that gives us angular velocity, and gives us these two velocities related together. So more homework examples coming soon, but I'll do those in some videos.